Hey folks, welcome to this episode on enthalpy and physical changes in particular. So remember what a physical change is. It's a change in the substance form, meaning that its size, shape, whatever, but it doesn't change its chemical properties. So for example, when we take water, and we'll talk about water a little bit more in this episode, water can go from being ice to being liquid to being gas, but at throughout this whole process, it still remains as H2O. In this case, it's H2O solid. In this case, it's H2O liquid. And in this case, it's H2O gas, but it's still H2O, meaning that it's going to have very similar properties. So going from here to here to here, what happens is that the intermolecular forces, so the forces between water molecules, change, but the intramolecular, the ones that are bonding the hydrogen to the oxygen to the hydrogen, they stay the same. And as such, the actual properties, the chemical properties, don't actually change. So in terms of physical changes in systems, there are two that we're going to be looking at. One is called dissolution or solubility, and the other one is going to be phase changes. So when we look at enthalpy of solution, this is a physical process. To dissolve something in something else, it is a physical process. Salt, if we put NaCl into water, it still remains as NaCl. Now, it changes a little bit, the properties change, because remember, salt as a solid does not conduct electricity, but when we put it into water, it does. And that's just because ions are created and they're able to move based on a difference in charge. But when we dissolve salt into water and we, for example, evaporate the water after, we get the same salt that we had before, and there's no change in the actual chemical properties. Now, to dissolve salt in water, for example, it's a three-stage process. Number one is that the bonds or the intermolecular forces between the molecules of the solute, the thing that is being dissolved, in that case the NaCl, they're broken, and this requires energy, so it's called endothermic. The next thing that has to happen is that the intermolecular forces between the solvents molecules are broken. So this means that here we have this thing of water, and the salt kind of wants to get in. So the salt has to break up first into its little bits and pieces, but that also means that the water has to kind of allow for space for this NaCl to get in. And then eventually what happens is that they mingle together and they form new interactions. So in that case, the Na plus, and the Cl minus interact with the water and they form new interactions, and that will release energy, and therefore that is called exothermic. So how does water, and remember that H2O looks like that. Now if you remember, water is in fact a polar molecule, meaning that the oxygen, let's put the lone pairs there, the oxygen pulls electrons towards it from the hydrogen, making this oxygen slightly more negative than the hydrogens. Now overall, this molecule is a polar molecule. The oxygen side of the molecule is slightly more negative than the hydrogen side of the molecule, which is slightly more positive. Now I'm just going to redraw this water molecule as something that looks like that, just easier, no oxygens, no hydrogens, no bonds, and anything else. Remember that this side above here is where the oxygen is. This is going to be slightly more negative, and this side over here is going to be slightly more positive. So let's say, for example, we had Na plus and Cl minus. Well, if we had these water molecules, the positive side of the water molecules will be attracted to the Cl, and the negative side of the water molecules, the oxygen side, will be attracted to the Na. And remember that this oxygen is the negative side, the hydrogen is the positive side. And so they'll orient themselves like this. Now the interactions that are formed over here, these water molecules are polar, they have a dipole, and these are ions. So what's going to form is ion-dipole interactions. So again, here's just this process visualized. So again, the solute has to break up, the solvent has to break up, they mingle up, and then they produce a solution. Now these again are endothermic, and this process is usually exothermic. However, sometimes it can be exothermic as well. The difference, however, sometimes is exothermic and sometimes is endothermic. So again, the difference here and here is between how much energy was put into breaking up the solute and the solvent versus how much energy was released when these solute and solvent particles mixed and formed a solution. If more energy is released when this solution is formed than put in, this is going to be an exothermic solution. And what you'll find is that the beaker that you're doing the solution feels actually kind of hot. Whereas in here, when we produce the solution, it releases less energy than was initially put in. And so in this case, you're actually going to feel a beaker that went from a normal temperature or from a standard start temperature to something that is actually a little bit more cold. And we'll do this in class. You'll see this. It's actually kind of cool. The other type of physical change is a phase change. So phase change is when you're going from solid to liquid to gas and plasma, and there's other forms of matter as well. And this all has to deal with adding or removing energy. Now we can go back to a very, very younger grade and say, well, how do we go from solid to a liquid? And think about ice. Well, if we leave a solid piece of ice, a solid piece of water on the counter, it's going to absorb energy and it's going to turn into a liquid. That's called melting, or we call that fusion. And if we take a liquid and we add even more energy, it turns into a gas, just like we do when we boil water for tea. Now, if that gas is left, and just like we see in summer days, when it's a little bit cooler in the morning, we see that gas condense into dew or liquid water on the grass. And then when winter comes around, that liquid loses even more energy and it turns into a solid. Now we also have these special states where solid turns to gas and gas turns into solid. But the key thing here is that as we're going from solid to liquid to gas, we are increasing the energy of the system. Okay, so we're increasing the enthalpy, which means that energy is leaving the surroundings and going into the system. Now, on the opposite side here, when gas goes liquid, liquid goes into solid, what we're doing is we're losing energy into the atmosphere, which means that the enthalpy of the system is decreasing. Okay, so if the atmosphere increases energy, that means that energy had to come from somewhere, and it's these gas particles that are losing its enthalpy to turn to liquid and to a solid. So recall that even though this is happening, these gas liquid particles are still the same thing. It's liquid water or solid water, aka ice, or gas water, aka steam. But they're all water, and so that means that it is a physical change. So we've seen this before as well. As we go from solid to liquid, we're going to have our delta H of fusion, and then delta H of vaporization, aka melting, or in this case, vaporizing. Now, if we went the other way, condensation, we're going to call this as the negative delta H of the vaporization. It's the opposite here, but you might see in some textbooks or some other resources that it'll be called delta H of condensation. When we go into freezing, okay, we're going to call it the negative of the delta H of fusion. But again, sometimes you'll see the delta H of FRE, aka freezing. Now, sublimation is going directly from solid into gas, and we call that delta H of sublimation. Deposition, which goes the opposite way, is just going to be the negative delta H of sublimation, or sometimes you'll see delta H dep. So again, we've seen this before, that the freezing and melting are actually the same thing. So when delta H fusion is positive, we call that melting. So again, that the enthalpy is becoming positive, the enthalpy of the system. Okay? The system is gaining more enthalpy, aka remember what enthalpy is? Sum of potential and kinetic energy. So if it's positive, that means it is gaining more enthalpy. It means that energy is going from the atmosphere into the system, and that means that the system is gaining, aka positive. The only way that it can go from solid to liquid is by breaking some of those intermolecular forces, and that is done by increasing the potential energy. Remember, bonds, the intermolecular forces, are all about potential energy. Now, if it's negative, that means that the system is losing enthalpy, and that means it's losing some of its potential kinetic energy into the atmosphere. Okay, and as a result, it has less. It has less energy for itself, and that means it is going to be freezing. So they're the equal magnitude, but opposite signs. The same thing is occurring for vaporization. When it's positive, that means it's increasing its enthalpy, it's gaining energy from the atmosphere, or from the environment, entering from a liquid to gas. The opposite is true when it's negative. It's going to be losing energy into the atmosphere and condensing, meaning going from gas to liquid. Same thing, they have the same magnitude, but they have opposite signs. So a little tidbit of information here is something called latent heat, and latent heat is just really called hidden heat. Now, why is it hidden? Well, at this point, when something has latent heat, it means that adding heat to, for example, water, at this point doesn't actually change the temperature. Okay, so we can add heat to a liquid water, causing the temperature to increase until it reaches a certain point. And even though heat is continually added, there's not going to be a temperature change observed. Now, when do we see that? When do we see a point where states change? Well, if we think about water, we know that 0 degrees is our freezing point, and 100 degrees around there, as Celsius we're talking about, is our boiling point. So we're going to see latent heat over here and over here. Now, when we pass this freezing point and we start adding temperature to water, think about it as in a kettle. Once ice has turned into water, water can actually absorb a ton of heat. And all that's going to happen is that the temperature is going to increase until it gets to a certain point where it starts still absorbing energy, but what we see is a phase change. At that point, there's going to be a plateau, and we'll see that a little bit later. At that point, we're going to talk about latent heat. So what does latent heat do? It actually allows us to break the intermolecular forces between these molecules. So when we talk about 0 degrees Celsius and we're adding energy to ice, what we're doing at that point is that we are adding energy, but that energy is going into breaking these intermolecular forces. Now, after some of these intermolecular forces are broken, we call that water liquid water. And we can add energy, and this liquid water can start increasing in kinetic energy, blah, blah, blah. It starts moving faster, but it's still liquid water. We still see it as a liquid until we get to a certain point where the intermolecular forces that are remaining break apart. And that point is going to be 100 degrees Celsius. At that point, we turn liquid water, into still water, but in this case, it takes on the state of a gas. And we'll see that it will move a little bit different because it doesn't have any intermolecular forces between it. So again, at this point, the added heat is not used to increase the kinetic energy of the particles, but rather used to increase the potential energy, aka we're going to be looking at these forces here that are keeping these things together. This causes the hydrogen bonds that are keeping the water molecules to break, allowing them to move into different states. So when we look at here, the energy that is required to move a substance from a solid to a liquid or a liquid to a gas depends on the mass. So we use this equation, E is equal to ml. M is the mass, and L is your specific latent heat. Now, specific latent heat is the amount of energy needed to change the state of 1 kilogram of substance at a constant temperature. Okay, so what that means is that, let's say for example we have this solid and we get to a certain point. To melt 1 kilogram of ice at 0 degrees Celsius, that's its melting point. Okay, its melting point. We need this amount of joules for every kilogram. Okay, so again, specific latent heat refers to a specific mass, and that is 1 kilogram. So this amount of energy has to be absorbed to break the intermolecular forces of the solid and make them into a liquid. Now, when we look at how the specific heat of vaporization, this is at 100 degrees Celsius, for example, liquid water, and that value is 2 million. Here we have 300,000, here we have 2 million joules for every kilogram. So this liquid has to absorb this much amount of energy to actually break the remaining intermolecular forces and turn them into a vapor. Now you can see this is a tremendous amount of energy compared to this, which allows us to understand why, solid goes to liquid before liquid goes to solid. For a liquid to go into a liquid to gas, for a liquid to go into a gas, it has to absorb a way more amount of energy than it has to when it goes from solid to liquid. So this is what we call a heating curve of water. We're going to just be looking at water this year, but you can see that there are particular areas of this curve. We can see here, this is temperature of the water versus the amount of heat added. So as we go this way, we are adding heat. But what you notice is that in this first part of the solid, as we add heat, the temperature increases to a point where we're still adding heat, but there is no change in temperature. This is where we see our latent heat. Okay, that hidden heat. We're still adding heat, but we don't see a change in temperature. After we get to a certain point, we keep adding heat, and that heat causes the temperature of the liquid to increase. Then again, we hit a certain point, look at that, 100 degrees Celsius, where we're still adding heat, but there's no change in temperature. And finally, we get to a point where we can continue to add heat, and the temperature goes up. So this first part is when we have water as a solid. It still stays as a solid, and we're adding heat, and we're seeing an increase in temperature from, for example, -40 or -25 degrees to about 0 degrees. And the heat that is added here is actually increasing the kinetic energy of the system, of the actual water molecules that's making up the ice. Now remember that when they're so close together, all they're doing is vibrating, okay? So they're in this structure here and they're vibrating. And so we're increasing the vibrational motion of these particles. Now again, we get to a point where we won't see a temperature change, but until we get to that point, we see a change in temperature. The amount of heat required to raise that temperature is determined by the heat capacity of the ice. And what you'll find is that ice, liquid water, and steam have different heat capacities. For ice can absorb 2.03 joules per gram degree Celsius. Now this value will be important later on when we get into some calculations. Now after it reaches about 0 degrees Celsius, we get into this latent heat portion. So heat is still added, but we don't see any temperature change. And that is because the heat that's added is increasing the potential energy of the system. Not the kinetic energy, but the potential energy of the system. And that's the energy associated with the intermolecular forces holding the molecules together. So to break the intermolecular forces that are holding the water molecules in a very crystallized structure in ice, we have to add energy. How much energy? 6.01 kilojoules, which is the molar enthalpy of fusion of ice. Okay, so the molar enthalpy of fusion of ice. So again, this energy is taking and breaking in the intermolecular forces that hold the water molecules together. So at this point over here, what's happened is that the intermolecular forces have broken up to a point where water doesn't take on a crystal pattern, it takes on a more liquid pattern. So at this point, when we add energy, or when we add a little bit more heat, we see an increase in temperature. So again, as we go through the process, we're still adding heat, and this heat is actually increasing the kinetic energy of these water molecules. So as we add more and more and more and more heat, these water molecules are moving more and more and more faster. Again, how much heat depends on its specific heat capacity. So the heat capacity of water is 75.3 joules per mole degrees Kelvin, or 4.184 joules per gram degree Celsius. Hey, we've seen that number before. Okay, so in this case, water, if we refer this back to ice, water has to absorb twice as much energy to increase the temperature by 1 degree Celsius of 1 gram of water compared to ice. And just like in ice, we see that it's increasing the kinetic energy over here. Again, there's still some hydrogen bonding between the water, but these water molecules are moving a little bit faster, so they're moving a little bit farther and farther and farther apart. They're still held together by hydrogen bonds, but hopefully if we add a little bit more heat, something will come of those. And sure enough, we get to this point where we add heat and we don't see any change in temperature. So we get to about 100 degrees and we see that as a constant temperature, even though we're adding more and more heat. And at this point, we've gotten to the molar enthalpy of vaporization, 40.67 kilojoules per mole to be specific. So what this means is that this energy that's being added at this point without any temperature change is going to break the remaining hydrogen bonds that are keeping these water molecules together. And you can see that here we have these hydrogen bonds keeping the water molecules together, and eventually, as they break apart, they become these little gas molecules that are free from one another, and they escape into this gas phase. Now, you can see that the enthalpy of vaporization of water is 40.67, and the enthalpy of fusion of ice is 6.01 kilojoules per mole, meaning that if the heat input is constant, a much longer period is needed for 1 mole of water to evaporate than the time needed for 1 mole of ice to melt. And finally, we get to this phase over here where the hydrogen bonds are broken between the water molecules, and they are now in the gas phase or the steam phase. And any kind of added energy here is going to be used to increase the kinetic energy of these gas molecules. And so these movement of the gas molecules will move as predicted by the kinetic molecular theory, the KMT, with increasing temperature. Okay, and the specific heat capacity of steam is 2.01 joules per gram degree Celsius, which is very similar to that of ice. Okay, so here's just a summary of what we see. The typical enthalpy changes are in a very, very small range. We'll see as chemical and nuclear changes go by that this value of enthalpy change is going to be a lot more, especially when we take a look at nuclear changes. Thanks very much for watching. See you soon.